Hi everybody, this is a quick training video on how to run your samples on the ImageStream MarkII. Told people forever, it takes about an hour to get the instrument started. So before you get here, call us. We'll get the instrument started for you. So when you get here, this is how you'll find the software. We'll have a series of tests over here. This is the assist test. If you see a bunch of green bars across the board, it means everything is running smoothly, so you can jump in and start your experiment. So we're going to do a couple of things before we start running our samples. You can see right now the beads are running smoothly, so the speed beads are always continuously running through the instrument. What I want to do before I get started is set up a spot where we're going to save the data that we're going to acquire. We're going to do that using the right-hand side panel under file acquisition. You have the file name. This is going to be the name of your data file. This is just an increment tool. And then this folder icon here, if I click on it, this window pops up, and this is where we decide where to save the data. Now, to be able to transfer your data on the server automatically, we recommend saving the data on the C drive, user, Avnis, My Documents, ImageStream MarkII data. Whatever ends up in this folder gets pushed to the server every half hour or so. We're going to make a new folder here with my name, today's date. And that's what we'll have over here. Next thing we'll do is decide what laser we'll need to use for this experiment. Today I'm just going to run a bunch of beads. We're going to run beads staying with P and APC. So we'll need the 48 and 642 laser, or 561. These two lasers are collinear, so you can use both of them on your P molecule. Bright field on channel 1 and 9. Let's use side scatter just for fun. The laser power, I have no idea what it should be at this point, but typically I'm going to start with the highest value and lower the laser power to, in case I'm saturating my detectors. Magnification is next, 20, 40, 60x. For this training, we'll use 40x. It really depends on what we're looking at. And the fluidics, I recommend the lower pressure. It gives you a sharper image in general, or more of the sharper image. And then you have your controls of the beads over here. Let's skip focus and centering. The software will take care of that. I'm going to start running my beads. I typically start with the actual sample. This machine will run 5 ml cubes. To load your sample, simply press the load button. It will bring down the loader or the portal at the front of the instrument, which we're going to see here. Everything takes a bit more time on this machine. There you go. Then I can simply put my tube in place and move on. Software is asking me how much volume do I need. Typically, you don't need all that much if you keep your concentration of cells fairly high. You should be able to run with 30 microliters and get enough events for your experiment. Click OK. Sample goes up, and in a few seconds, we're going to start to see data showing up. So the top window shows me each event that are crossing the laser beam. We see some of them are the speed beads, some of them are the actual beads I'm interested in. We're looking at the mix of single stain P and APC beads plus the negative control. With this window, there's a couple of things I can show you. So the first one would be if you want to stop the display, maybe you saw something that was fun, you can press the pause button and then scroll back up to see specific events that strike your fancy. It doesn't stop the actual acquisition, it just stops the display on this window. Second one is this icon here, the display settings. If you're having issues figuring out how the beads look in a specific channel, you can actually change the intensity of the channel by moving this slider bar here to change the way the beads are being displayed. It doesn't change the actual intensity that's being measured. It just changes the way it's going to present it on this graph. The other thing I can do here is change the name of my parameter. So channel 3 happens to be channel we're going to use to look at P. Channel 11 will be for APC. Channel 6 is going to be my side scatter. And this is all due to, it's all built in. If you find this on our website, you have the wavelength allocated to each of these detectors. None of these will be saved in your data file, so make sure you make a note of where each signal goes. Now we're going to start making some graphs, so that's what we'll use the lower image, the lower window here. Two type of graphs you can do, scatter plot and histogram. So we're going to use scatter plots first. There's a tons of features we can do here. I'm not entirely sure what each of them do, so I'm just going to give you a quick and dirty way of making sure your position is going to be correct. So we're going to start with area on the channel 1 and intensity on channel 6. So area will be my forward scatter, or the equivalent of forward scatter on a regular flow stamper. The intensity is the equivalent of all these fluorescent channels that you're picking up on traditional flow. Because I'm a flow cytometry person, I like to start with that just because otherwise nothing makes sense to me. The axes are auto-scaling, meaning whatever shows up on the graph will actually change its scales to adapt to the size of the event. So as you get more and more data, eventually the scales get more stable and you can start working. So we get different things you can see here. Probably a bunch of noise at the bottom. These are my speed beads, and these are the beads I'm interested in. So what I want to do is use these tools to draw regions on the cluster of cells I'm interested in. This R1 gate I'm going to call beads. And if you don't believe me that these are the beads, you can actually go at the top page here, and under all, I can now select the bead region I just selected and see what these guys look like. So they're much bigger. They are actually staying with APC and P. And so that should tell you that these are the actual beads. If you want to double check on the other clusters of events, I'm going to leave that at R1. And then if I go see what R1s look like, then these are the speed beads. They're much smaller and very low intensity on any of these other channels. Get rid of R1 and move on. Next graph we're going to use is going to be to discriminate against doublets or clusters of beads. I'm going to use area on channel 1 against the aspect ratio. And I forgot under graph properties, you can apply this bead gate here by clicking on the gate within that select population window. Now the only events are going to show up here are going to come from my bead region. You can see a cluster of events here. These are the single beads. The outliers are my clumps. I'm going to select single cells. Again, can go back here, make sure that all I'm doing is looking at those singlets. If you want to double check, again, R1. R1, we should see a bunch of clumps. There you go. So these are all doublets or 4 beads and so on. All right, next window, we're going to use a histogram this time around, and I'm going to use something called the gradient RMS on channel 1. And here what we're trying to do is get all the pictures that are in focus. So the cells are not always running exactly at the focus point generated by this cytodynamic focusing. Some images will be very sharp, very great to use. Some of them will be kind of fuzzy, and you don't really want them in your analysis. So what we're going to do is basically tell the software to discard or not count these events going further. So I'm going to make a gate. This is typically for acquisition. I'm going to make a gate that's fairly liberal. I'm going to call this in focus. And these, like anything between 45 and going above, is probably good on the 40x. If I go show you again, these are fairly in focus events. If I go back and I navigate on the events that are at the lower end of this gradient, then you'll see that these events are all fuzzy looking and not very sharp, not very in focus. There you go. And lastly, we'll do a graph to look at my two parameters. So here we're going to use the intensity of P and ATC. A few other features to look at. You could actually look at it at this point. Now, the question is, am I saturating the detectors? Are there any events that are too bright? One indicator that you are actually saturating your detectors if you get stuff like this. Whenever you get these cyan dots on your images, that's simply a measure of the signal is too bright for your detector. It's saturating it, so or the camera, I should say. So it's saturating the channel, so you get these dots. Same thing on the side scatter. So this is something you want to avoid as much as possible. So the only way to fix this on the image stream, we don't have PMTs or ADPs, so you can't play with the voltage or gain on each of these detectors, but you have our cameras, which will basically just capture whatever shows up. So what we're going to do, instead of playing with the voltage on that end, we'll play with the laser power. What we want to do right now is reduce the power on my P. So I'm at 200 right now. I might bring that down to 50. Side scatter, we're at 20 milliwatts. We'll bring that down to, let's say, 5. See how that looks. The refresh button over here. In some cases, I still have a cyan dot. It seems P is better. A better tool than just visually look for cyan dots is actually we'll make 3 more histograms. using a feature called the raw max pixel. So basically what this does is looks at the entire image and gives you the brightest pixel within this image. And if it's too bright, it's going to be at the very end of your axis. And if you have a bunch of these piling up in the very high bin, then you know that you're saturating, lots of your events are saturating your detector. You want to change uh, the voltage at that point, the laser power at that point. We'll make one for APC, one for, whoops, max pixel APC, one for E, one for the side scatter. So this looks pretty good at this point. I don't have on the TV, I don't have that many events piling up. Increase it a bit. Again, as in flow, the important part is going to be to make sure you have separation between your positive and negative fraction when you look at your markers here. Um, and side scatter seems to be pretty high still. I could bring that down 1 milliwatt. Truth be told, I don't care at all about the side scatter of my beads. So I might just leave it as it is. Obviously, if you change the laser power, if you go back here, you'll see the population move. So I can readjust my gates simply by pressing this move resize region. It will allow me to adjust the gate. At this point, we're just going to go ahead and record the events. In general, you could select a specific population of events to do your counting. So that's what we're going to have here. Count tells the software how many cells needs to be counted before we stop the acquisition. You're going to gate from either all of the events or a specific gate. If you have a population of interest that you need to study, you might want enough of these events to do proper statistics. And so in that case, you might say, I want at least, say, 10,000 events of cells that are in focus, so maybe stay in a specific way, or maybe that have a specific feature. So that's what you're going to decide here. Collect, since these two these two boxes are linked, we're going to count 10,000 events and save, stop acquisition, and save only what's in this region here. I don't like to throw away data at this point of the acquisition, so typically I'm going to either record everything or just the beads if I'm very sure that I'm not losing anything that's going to be useful later on. This used to be a problem where data storage was expensive. It's not the case anymore, so really we don't really mind. Go ahead and acquire at this point, and then we're going to basically let the software record all of the events that we want to in our data file. You have the counted region over here and the collected, so what is being saved in your data file. Normally, you're going to reach that limit and the instrument will stop the acquisition on its own. Obviously, we don't really want to wait that long here, so I can actually stop manually and I'll tell the software what to do with the data already saved. I'm going to save it for now. You can also discard it if you made a mistake. You want to restart your acquisition. We'd be done with the acquisition, so let's skip. We'd skip to the next sample. Right now, what I want to do is run my compensation controls. before I do that, I'm just going to explain what happens when you play with the remove your sample from the instrument. The injection here is through a syringe, so you can actually recuperate or get back the sample that you initially injected. So right now there's about 155 microliters. Makes no sense. Wait. There's some volume available in the tube, so I can actually ask the software to return it to the tube. I can also just tell it to dump everything in the waste, which I'm going to do right now. Then remove the sample from the instrument, press OK. The portal goes back up. It's going to clean the probe and wait for you to run the next sample. The next thing we want to do is run the composition controls. I just had the one sample today. Composition needs to be done even though the two markers here are not overlapping. You still want to do that pretty much every time you run an experiment. Computation is done on a pixel by pixel basis. It's not something you can actually do manually. We can attempt to do manually at all. So what I'm going to run are the same beads stained with a single marker, one after the other. So we're going to run again the same 30 microliters. And there's one specific thing I need to do before I record these composition controls. The first thing is I want to turn off my bright field as well as my side scatter. All we really care about is the signal coming from these fluorophore, and you really don't want those the bright field and the side scatter to interfere at all. So session will start in a few seconds. Eventually, I'll have my controls back. What I'm going to do is all right, there you go. So we're running APC beads, single stain control. What I want to do is turn off the side scatter as well as the bright field. I'm going to put that at the off position. And now, obviously, if I refresh, I'm not going to see anything. So my entire gating strategy is kind of not working anymore. So all these graphs will be used just to record my composition control. So what I'm going to do is make a new graph. I'm going to look at my intensity, the intensity of E and APC. But this time around, I'm not going to gate it on anything. We're going to keep it on all of the events. And we have here APC signal and all the beads. I'm just going to gate these guys here. R1 is fine. Change my count 10,000 R1 region. This fire here. And this composition control, you will be able to recognize it because the data file that gets generated gets this suffix called no BF. And we're going to stop the acquisition early, save the data. At this point, you would just run all of your composition controls pretty much the same way. Once you're satisfied with the way things looks and you're ready to go, you simply can turn off the instrument if you're the last one in the day. Gonna take the sample out. So at the end of your run of all the samples, you're asked to remove the sample valve, clean the probe, and then the software will bring the portal down again, and you'll be asked to run another sample. At that point, we'll just click cancel. And see, everything takes a little bit longer on the image string. Okay, so we'll click cancel at this point. We're done with the experiment. The instrument thinks it's an error. Okay. And to conclude, we'll simply press the shutdown button. Simply, the instrument will do its own routine to clean itself and sterilize. Click OK. This takes about 43 minutes. And at the end of it, the instrument will shut down. The software will shut down as well. So you can actually walk away at this point. You're pretty much done with the machine. All we ask is for you to enter the time that you actually use running samples in the logbook that's next to the instrument. That's what we're going to use to build time. We build time based on the amount of time you're actually using and not the startup and the shutdown time. That's all for me today. If you have any questions, give us a call. Otherwise, see you later. I thought that was beautiful.
What was that?
I thought that was beautiful.
Yeah, yeah.